So today is gonna be day 3 of learning C++. I took a break about like a month, so I'm trying to get back to it. So today is gonna be we're gonna go back to day 3. So day 3 is we are gonna continue going through the Learn C++.com book. So that's kind of what we're gonna be doing today. And I think we're gonna do 2 chapters today, because today the first chapter 3 is around debugging, and then we might just breeze through it, and then we could jump into chapter 4, which is about fundamental data types. Yeah, so I took about a break. Hey Mark. So Saturday mornings I try to learn something new. So what we're doing is learning C++. But then on Monday and Thursday, maybe Wednesdays now, we continue doing Go. So today we're taking a bit of a break from like doing Go to doing C++. But yeah, so that's kind of like what we're being up to. Yeah. So the goal is to like learn something new on Saturdays as part of the stream, and then the rest of the streams will be just like doing some Go around, like fixing some bugs in the streaming software or anything else that comes out of it. Even one thing I've been considering is working on a framework, like a service framework, but like I'm still thinking about it, so we haven't made much process there. But yeah, so today we're gonna be learning a bit of C++ debugging. I'm gonna just probably brush through it, since like most of the time I just use print statements for debugging. But yeah, we can just go through it and see what we can learn from here. Okay, so these ones are syntax errors, which we have seen a lot of them, right? Most of the time I'm missing the semicolons. Yeah, so sometimes I do this a lot. So that's one of the issues that we face. So then the other one is dividing by 0, which is pretty easy to figure out. Then when there is no initialization, you also get an error, which we saw in the past 2 streams. Yeah, so there's nothing much here. It's just mostly of the syntax errors that you could get from C++. And then there's one here where it returns, and this never gets executed. Okay, yeah, so I'm just gonna brush through some of this because it's not so bad to figure out some of them. Okay, so general approach is for debugging. Find the root cause of the problem, usually the line of the code that is not working. So the line, you mostly want to find the line that's not working, ensure you understand why the issues occur. Okay, so pretty basic stuff here. And then it's gonna go through samples, strategy for debugging. Yeah, so I'm gonna just brush through all of this. Strategy. Yeah, I'm gonna skip it. I don't think we should go through the whole thing, because like we would face these issues, and then we could get back to it. And I'm not using a debugger. So since I'm using Vim, I don't have a debugger attached to it, so this wouldn't work either. Okay, so I'm skipping that. We're gonna do chapter 4. Okay, introduction to fundamental data types. Okay, so there is bit size. The following picture shows some sequential memory addresses along corresponding bit data. Cool. So this is kind of how the data is stored. So their structures are stored like this in memory, and then when we access it, if we use pointers, we are just pointing to the address where the data might be. Cool. And then some of the data structures that C++ has are flows, doubles, and long doubles. And then we have charts, W charts. I think this one is used for like characters that are not part of like Chinese characters, for example, or Japanese characters. And then there's new ones. So we have 16 and 32 bits. So I think the Japanese characters are 32 bits. So probably char32 is an alias for wchar, so we might have to figure that out later. Then we have integers, short, and long, and long. Cool. Then here, so I believe this is one are for the null pointers, and then boy, which doesn't have a type attached to it. So most of the functions have boy. Oh, there is something about the T. I missed it. The T surface. So this one here and this one's here. Many of the types defined in new version of C++, null pointer underscore T uses this T surface. This surface means type, and it's commonly nomenclature applies to the modern types. If you see something with the T surface, probably a type, but many types do not have T surface. So this is a consistent apply. Okay, so I guess the new standard, the new types that were added in the new standards have that T at the end of it, but most of them don't. So it's like inconsistent. Okay. So the boy type is used for when a function doesn't return anything. So this is just telling the compiler that there's nothing to be returned. And if you try to return something, it's just going to throw an error. So I don't think. Okay, so I need to figure out this more. It says that it's deprecated. So in C, boy is used as a way to indicate that a function doesn't take. Oh, okay. So this is using boy as a argument. As a param. It looks like that's not supported in this deprecated in C++. So it's fine. Okay. Object size and size of operations. Cool. So this is the different ways that the data is represented and the different possibilities of them having like on and off in different places. Fundamental type sizes. Okay. So because we could use typeof, so typeof gives us the size of the type. So some of them take more space than other ones. This is helpful to know how much space your program is going to take. So you could look at it and you could be like, okay, so this is going to take 8 bits in memory because we're using a double or something like that. So some of them only use 1. So this one's use 1, 2, 4. So these are the new types. This one uses 2, 2, 4, 8, 4, 8, 8. Yeah. So depending on what the type you want to use, you might end up taking more memory. So you should be mindful which one you're gonna use. If you need extra space, so if you need an extra precision, you have to. The question you should ask yourself is, do you need the extra 8 bits versus just using 4 for a flow or just 2 for a end? Hey, how's it going? Is it flappy yet? Hey, flappy yet. I think that's the right way to pronounce it. Cool. So we could try this out. So we could try the different operations for. But I'm just gonna copy this here, and we could try to run it and see what we get in our program. This. Ah, cool. Good luck. Okay, so yeah, so because we are using typeof, we are able to see different we could see the different sizes of the types themselves, and how much space they're going to be taking in memory. So that's kind of what we see here. The long double takes 16 bits in memory. Cool. So yeah, depending on the machine itself, it might change over time. So the way that, if you look here, the person is getting for long double, he's getting 8. They're getting 8, and we're getting 16. So we're using double the memory here. And then for double, it's pretty much the same. And here too, right? They're getting only 2, we're getting 4. So it depends on the machine that you're running it on. So if you have, so I'm running on a Mac. So the Mac, I think is, well, they're using a 64 machine. So I'm not sure what the difference will be. I think it has to do with something with the processor itself. And then they introduced something, we should probably look at this more, because they introduced the /t, which is just extra space. Sorry, a tab, 2 tabs, and then we have a new line. So that's why it looks something like this. It's just adding 2 tabs. Okay, and then we are gonna jump into signed integers. The signed integers is if you have, I believe if you have negative, if you want negative, you do, I think it's sign, and if you only want positive, it's unsigned. Okay, let's see. When writing negative numbers in every life, we just, so yeah, negative sign. That's positive. So yeah, so it's sign. So since we are, so you could decide if you want to use sign or unsigned. I believe if you use unsigned, you get extra space, so you get more. You could store more integers. But the issue that happens is if you store a negative number, I think it just drops the negative part of it, or you might end up just having an error because it doesn't know how to store it. Yeah, so you could hold negative and positive numbers in. So pretty much all of them are signed by default, and you have to say when they're signed or not. So sure. The only thing I need to figure out is like, what's the difference between a sure and an int? So you could, oh yeah, so you could do sure and long too, and long too. This surface shouldn't use addition to. Yeah, so this is what they were trying to teach us. I still need to figure out what that is. Oh, right. Cool. So signed ranges. So yeah, so there's a range. I think. Oh, I see. So sure is 120 negative 128 to 127. So that's kind of what sure int is, and that's why it's in some cases the minimum 16 bits. So we have 16, which is bigger, and then it just keeps growing as it goes. These are not showing sign, so that's why you have the negative one. But the positive number gets bigger if you use unsigned. And if you run out of space, let's see. Yeah, I think if you run out of space, it's just gonna do some weird thing where it might cut off the number. yeah, so you get an undefined behavior where you might not get a number that you're expecting there. So like if you save, they say here 280, then you are going to assign. Okay, so it looks like C++ you're not supposed to use unsigned. That's interesting. Also supports unsigned integers. Unsigned integers are integers that can only hold non-negative whole numbers, which are just smaller. So here you could have like, so before we could only have 127. In this case, we could have 255 if it's unsigned. And like the numbers themselves just get bigger because we have more space now. Because we don't have to worry about the negative number, right? And because instead of having to, we need to use one bit to mark if it's negative or positive. In this case, we don't have to do that, so we can just use that extra space to store more numbers. Yeah, so we should keep this in mind. So sign just means it has a sign attached to it, so the negative sign. Unsigned just means that it doesn't have it at all. The integer is unsigned. Okay, so this is what I was trying to do. Oh, that makes sense. So Char doesn't mean what I thought it meant. So I thought it meant that we could use, we could only have like 127. But in this case, a Char just means like, I think it's just an integer here. And this is the max size of the integer when it's, yeah, this is the max size of the integer. If you run this one here, you see a wrap, which they'll give you a warning here. So they're pretty much just giving me a warning that is out of range because we're trying to save a bigger number. So the number doesn't fit in memory. So it's trying to be like, hey, something's wrong. And because it's too big, it's just going to return 0 and then 1 for some reason. Because it's wrapping. Yeah, so that's the behavior you get when you try to access, when there is a integer overflow. It just means that you lose a lot of information here. So first we ended up putting this number here, which is out of range, and then we got a 0, and we only went up by 1, right? So we got a 0, and here we went up by 2. So that means now that's why we got the 1. So the way to think about it is like the more you go out of range, the higher this number is gonna get, right? Because it just resets back to 0. It starts back from 0 after you get to the max number that is possible. Okay, that makes sense. That's why I wanted to see what happened when you went out of range, when you did a overflow. And this kind of what is showing here. It's possible to wrap. Oh, so you could go backwards too. So this number is unsigned. Yeah, so you have a short that starts at 0, and then you do -1, and then you start counting backwards. Which is very interesting because then it goes backwards by 2. So this is just pretty much cases of doing a overflow, an integer overflow. I see. So you're not supposed to call it an overflow, I guess. It's just called a wraparound. So I guess this is the overflow because you're starting again from 0, and this is the wraparound. Cool. Okay, many developers on some hard stuff. Okay, so I guess people at Google, engineers at Google, and other companies don't like using unsigned integers just because the behavior is different. So let's see. Oh, why is that? Oh, okay. So the reason why this is happening is, so we could try this one here. So I could see why that would be confusing. So if you do, I missed this here. Okay. So if you do something like this, I just noted that the title is wrong. This is day 3, not day 2. Okay. So the confusing part here is that when you do a operation on a number and the number ends up in a negative, you then get an overflow. So you get, 3 minus 5 is -2. And then since you get a -2, it's gonna wrap around. And then you get like this number here. And then it's like, wait, what happened? Why did I was not expecting that number. So that's kind of the issue with unsigned. Is that you end up, like, if you do any operations on those numbers, you might end up getting not what you wanted. Oh, okay, so this one is something else. So the first one is case 1. So like, so the first case was that we took an action on we did an operation on an unsigned, and then this one is different because we have a signed number. So we have, we have signed a -1, and we're passing it to a function that takes an unsigned int. And since it's -1, it's confused because like it didn't throw an error. So if you look at the compiler, when it's compiling, it's like, wait, what? So like, because we put -1 instead of x being -1, it's now just wrap around too. So the compiler itself didn't just throw an error when that happened. And like, this is an easy fix, right? Like if we did just int here, we would just get 1. Oh, sorry, -1. But like, since we're doing unsigned, that means that we are going to just wrap around because it just doesn't know the precision is lost completely. So that's kind of why they don't use unsigned. So I'm just gonna write a note that unsigned integers have 2 issues when you do any operations against them or you pass them to a function. Yeah, so if you pass a negative number to a function that takes an unsigned integer, or you do any operation and the operation ends up being a negative number, then it's just gonna wrap around, and then the number you're expecting is not gonna be the number that you want. So I could see why they would try to avoid unsigned. Yeah, so I didn't know that Java didn't have unsigned types. Okay, that's interesting. So yeah, now it makes sense, right? Why they will avoid unsigned integers just because of the wraparound. Because you don't want if you if let's say that you're running like a banking system or something like that, you are going to lose so much. If you have a negative, you end up with a negative balance, and the system is always expecting you to have a positive balance, like between 0 and and then but at some point you end up with negative 100 because you overdrew your account, and then that negative 100 turns into like a giant like $4 million. So now your bank account has $4 million by mistake because the negative number just ended up wrapping around. And it could be more than $4 million. I'm just using that example. Like here it would be like $2 billion or something like that. So that's kind of why it's mostly ideal to just not use unsigned when not necessary. Thanks. Hey SSB, how's it going? Yeah, you end up being rich. Like you end up being a billionaire because someone using an unsigned integer in your bank account software. Okay. Why is the size of an integer variable fixed? Short answer is that this goes back to C. When computers were slow, performance was at most concerned. He opted to intentionally leave the size of an integer open so that the compiler implementers could pick a size or int that performed best on the target computer architecture. Okay, cool, that makes sense. Cool. So this is just going over why integers themselves could have different sizes. So like the sample that we looked at before was that in my computer, this is 16, and the person that wrote the book, there is 8. So like here they have 8 instead of 16. Okay, so after a certain point, C++ introduced, or things, not sure if this is C++. Yeah. So the C++ standard introduced a new fixed width integer, which is just like making sure that we know the size of it, right? So the size of these types will not change. So if you use them, it wouldn't change over time. It will always be the same. So like if we use the plain ones, which we were using in here. So if we use something like Char, right? We don't know the size is gonna be when, depending on the computer that we compile it could have a different size. But if we use something like int a underscore t, then we will know the size of it. It's gonna be like 1 bit sign, and then 1 bit unsigned. And then pretty much the same way for everything else. So maybe, I'm not sure how you would decide sticking with these ones, with the new types versus using the old types. So it would be interesting to figure out if you stick with the new ones. And this is more to make it more like predictable. So how much memory your program is going to take across the board versus just like letting the compiler pick the sizes for you. But there is downsides, I'm guessing. The first is the... Oh, it looks like it has to support it. Hey, how's it going? Okay, so it looks like the fixed with integers are not really used unless the CPU supports it. If it doesn't support it, it's just not gonna be. It's not gonna compile in other languages. So the system itself has to support it. So that's kind of why people would just stick with the standard types. So that makes sense. But I think most of the maybe Windows, Linux, and will support that already. So I'm not sure if you should stick with it. So see what happens. Okay, so second, if you use a with integer, it might be slower than a wider type of some architecture. So there's a performance impact. So if you use the fixed with integer, there might be a performance impact for it. You might be tempted to use int a underscore t, but your CPU might be better at processing 30-bit wide integers. So you lose speed by making a restriction that is not necessary. So I don't think I'm gonna learn Python. Like I know Python already, so I'm not sure if you compare. But if you have any questions like that you go through, we could do that. Okay. Cool. Fasten. Okay, so there is a disadvantage to using with integers, so that I take my comment back. Maybe it's better to just use the standard ones. Just because like the way that is implemented, there might be a performance impact if we decide to restrict ourselves to int a underscore t. So maybe the best thing is just to just use the regular int type and let the system decide how they want to handle it. In that case, the size will vary, but that will be okay. Okay, fasten these integers to help address the above downsides. C++ also define two alternative set of integers. The fast type provides the fastest signed integer type with a width of at least nth bits. So in this case, it could be A, 16, 32, 64. So it lets you pick, for example, int fast 32 underscore t will give you the fastest signed integer type that is at least 32. So does that mean that it goes 32 and the 64? It might do that. The least type provides the smallest signed integer type with a width of at least. Okay, that makes sense. Okay, so the way it will work is that these two new types, fast 8 and then fast 16, fast 32, will give you the fastest one possible. But then if it's not there, it will pick the next one. So this one could go up all the way to 32. So if there's 32, we're just gonna pick 32, I think. Or 64. In this case here, it would just pick 8, 16, and 32, so it wouldn't go up. But if there is no 32, it will pick 16. I think that's how it will work. So let's write it out. Okay, yeah, so I'm gonna pick the list. Is there a 64? So 16. Which is not the case for me. Like they all match. That's interesting. So it says 8, 32, 32. So this is what happens, right? So in the case of the person that wrote this, they got 8, 32, 32, 8, 16, 32, right? In my case, I got 8, 16, 32, 8, 16, 32. So I didn't get a stack, because it didn't pick the highest integer. I ended up getting 16 here, right? Instead of getting 32, I got 16. So this might be something specific to Max, right? Where fast doesn't really give you the fastest integer. It just gives you like what you asked for, if it's available. And then like you get 32 here, 16, 8. So that's kind of the downside of this one too. So it's up to the operating system to tell you like to where you compile it to tell you like, okay, so you could use 32 here. In my case, I can only use 16, even though I have 32. So because you're doing that, it's up to the person that implemented the language itself, sorry, the compiler itself to handle this, the fast and the least. And it could just be very specific to the platform itself. So like if I run this in Linux, I might get these numbers here, or Windows, I might get these numbers. But when I'm using Mac OS, it just gives me 16 instead of 32. That's kind of interesting because like this doesn't even help at a point, right? If you're doing like, it will help in other operating systems, but it wouldn't help if you're using like a Mac. So I wonder why that's happening there. So I'll probably make a note to figure that out later. Yeah, that's very interesting because like it shows like, so this one here, when we use these types here, we're always gonna get the size for it, right? If the operating system and the CPU supports it, you are always gonna get the space that you're asking for the integers. But the downside is like if you have a operating system that supports 16 and you ask for 32, you're not gonna get the 32, which is kind of the downside there. Here, if you ask for more, there might be a case where you might not get what you ask. Like you might not get the fastest one either way. So that's kind of interesting here because like I will end up just probably picking. Depends how much I care about it, but maybe the fit width one might be the better choice, and at least in my case with the Mac. So it might be like an interesting state there. Okay, so there is an issue with int_a_t, which behaves like ints. So you could store integers in it. Wait, you could store characters in it. Okay, that is weird. So I wonder if this is the case in my computer. Oops. So because of how the standards work, some compilers ended up creating int a as a character type instead of an integer type. So when you run it, you might end up getting an A depending on the compiler that you're using. But I think since I'm using, so this is what happens, right? You get the letter A instead of 65. So my compiler has that issue. Oh. So that happens with, if we use int a_t. So yeah, so at this point, it's like if we use the fit weight, we will not be able to use 8 bits because we will get, instead of getting numbers, we will get characters, which is kind of a downside for it. Okay, int should be preferred when the size of the integer doesn't matter. Okay, so if you don't care about the size of the integer, we just use a plain one. If you need to variable guarantees to be particular size and want favor performance, use, so if you care about performance, we will use fast and then the number. If you need a variable guarantee to be particular size when favor memory consumption over performance. Cool. So if you care about performance, we go with fast. If you care about memory consumption, we go with least, which makes sense. Yeah, if you have a lot of variables, we will go with least. And then avoid unsigned. So we're not going to use unsigned because it's very unreliable when it comes to like wrapping around. We are going to avoid 8 bits because it's just a character at this point. Any specific fix with integer, for example, Visual Studio defines. Okay, so anything that has to do with compiler, because then if we want someone else to compile this on Windows, it wouldn't work. Sorry, not Windows, on Linux, it wouldn't work because those definitions will be missing. Okay, and then now the interesting part, which we've been kind of doing already, is we've been using typeof already. So I think we might learn a new typeof. So type underscore t. Consider file code. So yeah, so type. Well, I wonder what's the difference between type t and typeof. We can infer the operation sizeof returns an integer value, but what integer type is that value? An int is sure. The answer is the size of. And many functions that return a size of length value return a value of type. Okay, so this here doesn't return an integer, it returns a type, sorry, a size underscore t type. It's a defined as a unsigned integral type. It's typically used for representing the size of length of an object. Okay, so that makes sense. So typeof doesn't return an integer, it's just, it has its own type. And that type returns a value of the length of the object itself. Cool. So it's like you could reuse it too. So you could get like the type of the type in this case. So you could check the type of the type here. Okay. So yeah, today we are all going through like different ways of doing types and like how to handle like data, like numbers. So the next one is scientific notation. So like how do you represent a larger number using scientific notation to do that too. And it's just pretty much how do you represent a number like this using the scientific notations. So like multiplying it by the power of 10. Sorry, by a number, by multiplying it by 10 and the power of that number attached to it. But sure. So how do you store it? Let's see, precision and trading spaces. Oh, you could store it yourself, but then I see. So I guess the language already supports that. So if we do something like, if this works. I think if we do something like and we return 0, and then here we do that work. So Okay, so I wonder if this will work. So what I'm trying to do here is I'm trying to see the notation to see. I want to see if the notations themselves are just you could just use it anywhere. Nope. Let's see. Oh, okay. It has to be a double. Okay. So that worked. The only difference is it has to be doubles. I wonder if I make it smaller. Okay, so it has to be a double. Yeah, it has to be a double to be able to use scientific notation, which is okay. Just to mention it here. It does mention it in the comments. Okay, so it has to be a double. So you use scientific notation if you use a double, which is cool. Then let's move on to floating points. Floating points numbers. Integers are great for counting whole numbers, but sometimes we need to store very large numbers of or numbers with fraction components. So like if you need to do like 0.1 or 0.0, it could be a double. And then we could define a flow by putting this surface f on front of it. Always make sure. How do you decide between? Maybe something we'll figure out later. Okay. Always make sure that the type of your literal matches the type of the variable that being assigned to, or used to initialize. Otherwise, an unnecessary conversion result. Probably will lose precision. Okay. So we have to be careful. Because if we assign z to x, the 0 is gonna be dropped. And same thing if we go down, the precision gets worse. So we might end up losing numbers. So we might lose the 7 here. If we assign it to x, for example, if we assign it to this x here. Cool. Precision on it. So if you have 1/3, 1/3 goes infinitely. So you just print 3 over and over again with no stop. The default one for cout is 6 digits, so the precision is 6 digits. That means that if we do 1/3, we will get 3 digits. So we could try it out, right? So maybe let's just take this sample. So if we do something like this, right, where we're dividing 1 by 3, 0. Wait, where is the precision? Oh, so I'm gonna have to. Okay, I see what I did wrong. It's not a. If I have to print the zeros, so I'll have to do 0.3 for it to work. Okay, and then we could turn in. So that right now they're double. So if I believe I append f at the end, it will be floats. Yeah, so it's still 6. And then if I wanted to higher number, so if I want to increase the precision, I may have to use something like the precision. So I could set the precision to a higher number. Oh, this is interesting. So you can send. So it's like you're sending a config. Then you're setting you're changing the precision of cout. And then that works. Oh, I can include the namespace. I see. So in here. So this is a different header that has that information that we need. So IO man IP has set precision. So that's the set precision one is the one that you could use to set the precision. So you do something like that. We could increase the precision for it, but it gets a bit weird. It did, yeah. So the precision gets interesting because we're trying to go all the way to 16. So this is kind of how we set the precision for cout. So CL has a precision of 6, so we could control it by using set precision from the standard package, which is cool. And then you could just also cut it out too, so you could reduce the precision of it too. I'm not sure what it did. Some weird stuff. He rounded this one to 92 when it's only supposed to be like 89. Because we set the precision to 16. Okay, precision issues don't just impact fraction numbers; they impact any number with too many digits. Let's consider. Oh, I see. So because we're messing with the precision here, we threw the number off by a lot. So we lost the precision, and then we have a rounding error. So the rounding error here is like somehow 89 was turned into 92, and now you have a rounding error. Favor double overflow unless space is a premium. Okay, so we should always use doubles overflow if we have the space, because doubles are, I believe double takes more space in flows, floating points. Rounding errors make floating points go. So because of rounding errors, comparison is very risky here. Because you could get different numbers, right? It's like here we get 1, and then here, because we increase the precision to 17, we have this number here where it's 1 with a bunch of leading zeros and then 1 again. And then the bottom, it just throws it off. And we cannot compare it, right? Because it's not equal. So D here is not equal to D here, which causes some problems later on. And the rounding error happened here, right? We're rounding up for some reason. And then there's more rounding errors happening there. Rounding error occurs when numbers cannot be stored precisely. This can happen even with simple numbers like 0.1. Therefore, rounding errors can and do happen all the time. Rounding errors are not the exception. They are the rule. Never assume your floating point numbers are exact. Yeah, so floating points are very dangerous for banking. So here in this case, you might have a rounding error that takes you and give you like $3 or $4 because there was a rounding error. So if you're building a financial system, be careful with rounding errors. Okay, nan and inf. There are two specific categories of floating point numbers. First is inf, which represent infinity. Inf can be positive or negative. The second is nam, which stands for not a number. There are several different kinds of nan. Nan and inf are only available if the compiler uses a specific format. So if there is a specific format for floating points, then you can use inf and nan, which one is a 0, one is not. So dividing by 0 is a positive nan. Oh, that's interesting. Then dividing by 0 is... Oh, let's try this out. Okay, so... Alright, so here, because we're doing using a negative, we're dividing by a negative number, so we're dividing by 0 here. So if it... Wait, yeah, we're dividing by 0. Oh, we're dividing by a flow point. So we're dividing by flow point 0, which instead of just being like you cannot divide by 0, is saying, hey, this number could be infinite, positive infinite, and this number could be just negative infinite. So you could have infinite amount of numbers here, and this one here is just saying like this is not really a number. which is what's happening here. If stands for infinite, and ind stands for indent. Wait, did we get an and? Yeah, we got an and. We didn't get the second one. Sorry, we didn't get the last one. So I think there might be something to do with because I'm on Mac and the writer, the author of this book is on Windows. They got a different one. So they got IND, which stands for indeterminate. So when you divide by 0, it just becomes indeterminate. In my case, I just got nan. Okay. Avoid dividing by 0 altogether, even if you compile support. Yeah, you never divide by 0. Because the behavior is undefined across the board. Okay, and I think, let's see where we are. Next one we're gonna learn is Boolean variables, which is just true and false. And like you could do different operations against them. So you could have, you could also, if you put an exclamation point in front of it, it becomes negative, and sorry, it becomes false. If you do true, if it's false, it becomes true, which is one of the cool things. So, and then same thing with comparison. So in this case, true and false are printed as 0 or 1 by cout. Yeah, same thing here. So just 1 and 0. If you want the cout to print true or false instead, so you have to use another standard library to be able to do it. It's kind of cool that you could pass configuration to cout this way. I was not expecting that. So it's kind of interesting to see how that is being passed to it. Just because, like, yeah, it's just super interesting to see how that is supported. So that means like we could pass different configuration to cout to do actions, other actions that if it doesn't support it, we could teach it to do other things. So that might be cool to look at later on when we have more of a grasp on the language. We could figure out how we could do different things with cout. Yeah, so it's printing true or false, which is very cool. Okay, integers to Boolean conversion. You can initialize a Boolean with an integer using unified initialization. So you cannot really do that. I'm not sure why we do that. I'm not sure what's happening here. So, oh. Okay, this is weird. If you initialize it like this, it does use true and false. So any number that is greater than 0 is true. Any number that is less than 0, equal or less than 0 is true. Which is interesting, because like I'm not sure why this case didn't work, but this case does work. So when you initialize it, so I could see back in day 1 we were figuring out like if we should define variables like using the brackets or should we use the equal sign, and we ended up going for the brackets. I think the brackets are very helpful here because like this shouldn't be allowed, right? If the compiler is going to complain here, it should also complain here, but there might be historical reasons why it doesn't do that. Okay. Okay, so yeah, so if you're expecting true here, if you're using Boolean here, it might just be it's always gonna be true. I think because the memory is being allocated. Oh, so if we input something, it only assesses 1 and 0, right? It doesn't take anything else, and then it suddenly fails. Oh, so yeah, that's kind of dangerous, right? Because like, with something for us to keep in mind, is that if we put true, like write it as true, it's not gonna work. It's just gonna fail because it doesn't know how to handle it. It cannot assign it to B because B is a Boolean. And you could return Booleans. Okay. Then if statements. So if statements are very useful because then you could have branches. So you could do if this equals true or this equals false. You could do something else. So this kind of becomes very handy too. Like most programs are just a bunch of if statements all tangled together. There is nothing here that looks too complicated. If statements only coordinate execution single statement. We talk about how to coordinate executing multiple statements in lesson 5.2. Okay, so we could have if and else, right? So it could be if this is true, then do else, right? So pretty much this here. Is also here. Yeah, so we have if else. That's very cool. And you can chain them together. So you could have if this, else if, and else. You could also comparison. So you could do if this is equals to this, then you could return it. So that's very cool. And then you can just return that as a function. If all of the samples above okay, so in this case, if you do something like regular numbers or characters, it will always return true because it has a value attached to it. Sorry, I need a second here. Okay, and then there is characters. So there is the ASCII standard, which is just like how every character in the keyboard is represented. I think it's in the English keyboard, which is just pretty much why when we type 65, we got A before. This explains it, right? It's because the way it works is that when you use characters, they're turned into integers, and then those integers are turned back into characters. So like exclamation point is the code for exclamation point is 33, and then it just brings back the exclamation point. So that's how the conversion goes back and forth. And then there's like some characters that are used for special cases, at least the first 31 characters. Also, if depending on the, so like for example, capital A is 65, but lowercase a is 97. So like you have both sizes of it. Like you have the uppercase and the lowercase to represent the characters themselves. It becomes more, if you want to do like Japanese letters, it becomes more difficult because they're not part of these representations, so you have to store them differently. And I think that's why there's W char, the type. Let's see. So this will print something else. Let's see. Printing chars as integers via typecasting. So if you cast it, we cast the character here to int. So this is turning into an integer. Wait, where's it? Yeah, this is assigned to an integer. And then we just print it. So it's pretty much typecasting. So you're able to take a number. You could take a number and turn it into a character, or take a character and turn it back into a number. And the way you do that is by just adding the type the variable name, and then the character itself, which is kind of cool. And this is also like doing the static casting too. So this is just doing the exact same thing, which is also very interesting. So you're statically casting the type. This looks like we haven't looked into generics in C++ yet, but this looks like a generic syntax for conversion. So that's kind of cool too. So we're getting a hint of the C++ might support generics, at least the language itself. I'm not sure if we were able to use it yet. And that's kind of we will also see it here too. Okay. Char sizes, ranges, and the float signs. Char is defined by C++ to always be 1 byte size by default. A char might be signed or unsigned, although it's usually signed. If you're using char to hold characters, you don't need to specify the signs. In both signed and unsigned characters, chars can hold values between 0 and 127. Yeah, so we have 0 to 127, so that's what we really care about. So it could be either one. That's cool. Yeah, so it's always gonna fit, so it doesn't really matter. So you could escape to like new lines. Wait, is new line here? Nope. I see. Yeah, so then there's like, if you want to escape strings, you could also do backslash, like double backslash to escape it. To escape backslash, you do double backslash. To escape single quotes and double quotes, you do the backslash too. If you want to print them. So that's kind of a cool way to escape. And then we learned that we don't want to use endl because endl flushes to the terminal every time you run it. So every time you call this here, it will just flush to the terminal, so it's very inefficient. The best way to do it is backslash and which creates a new line for us. So that's how we end up creating new lines. What is the difference between putting symbols in single quotes and double quotes? So we know this from the first day. Single quotes are for characters, and double quotes are for strings. So a string literal is the language itself builds that for us. So at the end, this ends up being I think it's an array of characters, and this is just one character, for example. So that's why you decide how you decide between single quotes and double quotes. If you have like single characters, you should just do single quotes. Cool. So this is literal. So kind of how you represent like strongly type. Like how do you represent like the different types and things like that. So you could put it at the beginning or and in some cases. So like if you want to do unsigned sign. So like for 5u is 5 unsigned. So like this forces the compiler to know that this is gonna be unsigned. So like the 5 is gonna be unsigned. Yeah, so this is what we were talking about before. So when I created a decimal variable, I didn't put f in front of it. So at that point, the compiler just made it into a double, because it doesn't have the surface, like it doesn't have the f at the end of that 1.5. Yeah, and this is the string one. So this is how you create strings, which we saw before. Doubles and like all different things. You could use octa and hexadecimals as well. So it's kind of like going through the different types, how you define different types. We saw also before how we did scientific notation, so that's also a literal there. And then pretty much how you represent like the decimals and things like that. Yeah, so actually decimals end up with F. Wait, does end up with F? Yeah, I think you define them with F at the end. And you could do binary too. So like that's kind of a cool thing. Oh, okay. So it doesn't end with F. It starts with 0x and then the value afterwards. So that's kind of how you define it. This might become helpful later on if you want to do like any like hardware stuff. And then same thing here too. Oh, this is a new syntax. So by default, C++ prints values in decimal. However, you could tell it to print other formats too. Okay, so we could just tell it what format we want to print it on, which is cool because you're still passing the configuration to this to cout, which is something that I want to look at more. Magic numbers and why they're bad. Where are magic numbers? A number such as 30 as the 30 in the snippet 12 is called a magic number. A magic number is a literal, usually a number in the middle of the code that does not has any context. What does 30 mean? Oh, okay. So it's when you have a random number and you don't know what it means, like where it came from, right? To update our program using a new classroom size, we have to update the code 30 to 35. But what about the code to set 30? Yeah, so that kind of like throws it off. So you might want to use content values here by using definitions and things like that. So it kind of makes sense. Like this is what they call magic values, but it's just a bad value that you don't know why it's there. Like why are you multiplying classrooms times 30 and then set max to 30? Cool. Don't use magic number in your code. Okay, so I think this is what it's going to teach us, right? Is how do we create content values that don't change over time. So this is helpful because then you could define, like here, you could define gravity, and then you cannot redefine it ever again, right? It's like gravity is only going to be the same number over time. So you're not allowed to change the value for it. And then it makes it easier for you because you could just go back and make sure that you update the number here and you don't have to worry about anything else changing it over time. So it looks like you have to always initialize it. So it's like super interesting because then you don't have to worry about like, what if this changes or not? And then we're going to go between runtime versus compile time constants. So a runtime constant allows are for those initialized values that only be resolved at runtime when your program is running. Variables such as user age. So if we assign the value here, this is a runtime constant. If we define it like this, I'm guessing that that's a compile time constant. Yeah. So those who initialize this. Yeah. So if we define it at if we define it as star as part of the code, that means it's compile time constant and it wouldn't change. So and then you get optimized too. So like it probably just figures out where it's going to be used and then just swaps it. It does. So the compile time constants are changed over time. To help provide more specific, C++11 introduced the keyword unexpressed, which ensures that constant will be compile time constant. Oh, so you're pretty much giving hints to the compiler that this is going to be a compile time constant. So same thing here. And this wouldn't work. Wonder what happens here. Would it throw an error? It probably would take, yeah, it would throw an error. Naming. Some programmers prefer to use all uppercase name for constant variables. Others use normal variable names with a K prefix. However, we will use normal variable naming conversions, which is more common. Okay, so I usually just use uppercase too. So you pretty much just use that so we don't have to deal with magic numbers, so we know where the numbers are coming from. Objects like macros with parameters and symbols. So we decided that we're not going to use macros that much. So like here is you're using a macro for it. And it looks like it's bad practice to use macros. So yeah, it could be a bad idea. Consider our second example using fine symbolic. Yeah, so we are not going to use macros for defining constant values, which is kind of defining this here. Wonder if you could have constant values inside of the headers. Oh, you can. Yeah, so that's kind of how we're going to stick to it. So if we do this here, where we have it on the header file, we could just use them anywhere. And if you decide to use capital, this is where capital letters become helpful. Having everything in uppercase, you know where it is coming from. They're also using guards around here to be able to use, namespaces to protect it. And so you could define where it comes from. So let's see. Are they using it anywhere? Yeah, so like they are accessing it through the constant. So it makes sense. Okay. Cool. Okay, so this is the last part. I'm gonna end up the stream here. There is nothing else here. Yeah, so I'm gonna end up the stream here. Thank you so much for watching. I am now trying to stream Mondays, Wednesdays, and Saturdays to get back to it. So I stopped for a bit, so I'm trying to get back to it. So thank you so much for watching. I will see you Monday.